Okay, folks, we're back. Also, I'm here at the church where I've been recording. It's the middle of the day. We'll see how this goes. There's some pleasant background noise with the organist doing some rehearsal here. So we'll see if this is way too distracting. I hope it's not. Maybe it'll actually be kind of nice. Okay, so when we left off, the last thing we talked about was the solubility of oxygen in water. And the concept of, graphically you can see this, I'm just looking at the slides. So if you have the slides in front of you on your computer, which I don't have here, this is where we left off. And the idea is if the temperature goes up, well, just chemically, basically, the dissolved oxygen goes down. That's the trend of solubility in general. As the temperature goes up, the solubility of gases tends to go down. And the most important gas that we talk about in this class, or for this chapter, is oxygen, and we did some examples of VOCs before. Okay, so this is where we left off, and so we're going to end up here, going to letter C, and I'm not going to rewrite these notes on the board. So this is section 10.5, and this is a couple of sections on oxygen demand, and the first one we're going to discuss, it's kind of it's a good measurement. It's called biological oxygen demand, and you can see the definition. I mean, you can write that down or just look at it on the slide, however you're keeping your notes. I'm not going to rewrite this. So the amount measured in ppm, milligrams per liter, of oxygen consumed by oxidation of dissolved organic matter facilitated by various microorganisms. Okay, so what would that be? So something like farm runoff or leaves even in the fall when it's decaying organic matter or dead animals or dead plant material. Anything organic that goes into a water system is going to be digested by microorganisms. And how much of that is called the biological oxygen demand. Now, how is this done in practice? I think I'm going to have a slide for this later, I think I do. But it's actually pretty simple. You just get a dissolved oxygen probe or a dissolved oxygen test kit from like a toolbox or a tackle box, I call them, tackle box water testing kit, and you measure the dissolved oxygen in that sample. Then you store that sample for a period of time outside of the light to prevent any kind of photolysis in a buffered solution so the pH does not change. That's important. And you let it sit there for a while. Then you go back and you measure the dissolved oxygen again and see what happens. Basically, you're just giving the microorganisms in that sample a chance to do their thing. And then it's actually a pretty simple formula that you plug it into to calculate biological oxygen demand. But we're not actually going through that practical kind of thing here. We're just sort of looking at it from a big picture chemical standpoint. Yeah, and that's actually mentioned right there. So you measure the dissolved oxygen before and after in a pH buffered solution. Okay, so I just explained that. So in the lab, it's actually not that difficult of a thing to do. It just takes some time. And you can see there, well, what does it even mean? So if you have a biological oxygen demand of 1 to 2, okay, you can read those on your own on what that says about the water quality. So if it's a high biological oxygen demand, that means there's a lot of organic matter in there, so it's consuming a lot of the oxygen. The microorganisms are consuming the oxygen rather than just staying in there to promote the aquatic organisms. So that's the kind of thing you wonder, wow, the organ just really picked up. We'll see how this video turns out. Okay, so what I want to do is go through problem 10.4 with this one. And I'll just keep doing my show and tell here. Yeah, so more show and tell. You'll see in your slides there's a bunch of pictures here. I'll just kind of keep vamping or filibustering while the organ plays. So what are these pictures? I may have mentioned earlier in this course that I'm a trail steward out at a local lake called Possum Lake. So I'm part of the Friends of Possum Lake Conservancy. And I just keep a trail clear. But we have a real algae problem out there. In fact, this picture that I have here from last summer, there was so much algae and there were some species of algae that were producing toxins in the water. And they put out well, you can't swim there anyway, but they didn't even want people wading in the water, like going out and wading in there to go fishing or just having kids splash around at the edge of the water. And part of the reason was there's so much algae was in there is that took, when you have that much algae, typically that's because of fertilizer or other kinds of farm runoff, the algae starts to consume all the oxygen in there and it just snowballs and makes things worse. And okay, so we'll talk more about that later. Okay, so where are we? So this is letter C. Letter C, or letter number 1. So just a couple things here. So this is biological oxygen demand. And just recall this is a good number, is that the concentration of oxygen maximum is 8.7 milligrams per liter. I believe we calculated that in a previous problem. So that's the maximum solubility. And that's also called saturated. So when a water system is saturated, and this is at a specific temperature, I can't remember which one it is, I think it's like 20 or 25, that is as much as you're gonna get in there. And just to give you a couple of examples, the chart there tells you what's a good BOD, what's a bad BOD, if you will, but the median biological oxygen demand. So this is pretty good water. Fairly clean water systems, you're going to get around 0.7 milligrams per, now the units are different here, or milligrams per milliliter. And I'm not too worried about where that comes from right now, it's just a calculation. But if you have something like sewage, which is pretty nasty to think about. So sewage would have a huge biological oxygen now, somewhere sometimes around 110 to the second milligrams per milliliter. Okay, so the example I want to do with you is 10.4, and I think I have the problem stated in the notes, so you can either copy it down or just write it. I'm just going to go over the wording of it again myself. Here we go. Oh yeah, and the biological BOD method that I showed you before, there's an infographic there for that. I'm not going to go through that with you. That just shows you how you do a biological oxygen demand calculation. There's 2 different ways to do it. You can either just do it with a chemical dissolved oxygen test or with a sensor of some kind. Okay, so the problem here is, all right, show that a liter of water saturated with oxygen, okay, at 25 degrees Celsius, so I think that number works, is capable of oxidizing 8.2 milligrams of polymeric CH2O. Okay. We can't possibly consider every single kind of organic matter. That gets way too complicated. There's too many molecules out there. Think about the tannins from leaves or decaying animal matter, decaying plant matter. So what we do is we simplify things. And that's where I want to pick up with this problem. CH2O, polymeric carbohydrate. So, just a couple, why are we doing this? So, CH2O, that is a placeholder for basically organic matter. So, generic, polymeric carbohydrate. Now, that's going to make sense to a chemist if your chemistry background is a little weak, which it shouldn't be being in this class. This is more informally referred to as organic matter. So this is a symbol for organic matter that allows us to do a stoichiometric calculation somewhere down the line. So this is plant matter, animal matter, etc. Okay, so here's the deal. This is very important. So, in an oxidizing environment, now to this point, this is all we've talked about. We have oxygen around, therefore it is an oxidizing environment. If you go further down into, say, a lake, which we're going to give you a graphic for that later, the environment becomes, well, anaerobic because there isn't any oxygen, so that becomes a reducing environment. So right now we're considering an oxidizing or an aerobic environment. And well, what goes on there? Well, this is what's happening. You probably remember this from chemistry. You take a generic carbohydrate and it's dissolved in water. It's oxidized by oxygen. And we're going to assume complete oxidation. Oh, I'm sorry. This should be AQ, aqueous carbon dioxide, and water, which you could write as AQ because it's surrounded by other waters. That's probably the easiest way to do it. So this is called complete combustion. You take some hydrocarbon. This looks like combusting methane or combusting some fossil fuels. It's the same chemical equation. So you're just taking that and you're combusting it. And I don't think we have to worry about a lot of stoichiometry yet. Okay, so how are we solving this problem? I'm going to try to write this on one board. I've already taken up way too much space. So the first step in this problem, incidentally, these kinds of problems we've been doing in aqueous environment often involve the same tools done in a different order. So remember what we have here, Henry's law, and then we have stoichiometry and unit conversion. So that's really all we're doing here. This is not a unique problem that we're doing, it's just applied to a unique situation. So the first step we're going to do is apply Henry's law. And we know that Henry's law constant, we are not changing that. We're using that for all the same temperatures. There might be some homework problems, or I might put it on an exam where you use a different Henry's law constant. So we're not just doing the same temperature all the time, but we're just making a point here. So 1.3 times 10 to the minus third molarity per atmosphere. Go back and review that if you need to. And remember that we are assuming a partial pressure of oxygen of 0.21 atmospheres, which is consistent with the fact that oxygen is approximately 20% of the atmosphere. So 0.21, 21% of one atmosphere. And I think we've done this problem before, so I'm going to streamline this a little bit. And remember, Henry's law just says that the concentration of a dissolved species in aqueous solution is Henry's law constant times the partial pressure. I'm not going to do that. Just multiply those two numbers. You've seen that done before. And you end up doing that, when I did it, but do that yourself, just multiply them. And you end up getting 2.73 times 10 to the minus fourth moles of O2 per liter. Good. So now we've calculated how many moles of oxygen per liter, because the problem asks for 1 liter, so that's convenient. Well, how many moles of oxygen get in there? Well, 2.73 times 10 to the minus 4. Now we've done, I think we may have done that exact problem before. But, so step 2, my goodness, this is an easy problem. I have to come back and look at something here. Is this balanced? Carbon, carbon, 2 hydrogens, 3. Yeah, okay. So this generic oxidation equation for a generic hydrocarbon, so organic matter, everything here is a 1-to-1 ratio. The math here is much simpler than probably the problems you did with organic chemistry or with general chemistry for sure. So step 2, well, this sounds really familiar. Do the stoichiometry. And you may not need, I'll just map this out and stop the video if you want to. So this is pretty easy. You're trying to, what are we trying to calculate? How many milligrams of organic matter? So we want to know how many milligrams of organic matter takes place here. Well, this may be straightforward. So if you have 2.73 times 10 to the minus 4 moles of oxygen per liter in your system, and you have a liter, so you just multiply that by a liter, that'll tell you how many moles of oxygen are there. It's 1-to-1, that'll tell you it's the same number of moles of organic matter, and then just convert it to mass by using the molar mass of this if you want to get that. So it's, what is that, 12.01 grams per mole plus 2 times 1.001 grams per mole plus 15.99999 grams per mole rather than periodic table, I think that ends up being about 30 grams per mole. So it's really just a stoichiometry and unit problem at this stage. So this is kind of like a titration. You take the volume of your solution, which is 1 liter, in this case the solution is just your water sample, you multiply it by the molarity of whatever it is you have, 2.73 times 10 to the minus fourth moles of O2 per liter. It's a little sloppy, my apologies. Then you know from the balanced equation, 1 mole of O2 corresponds to 1 mole of our generic organic matter. And then 1 mole of generic organic matter is about 30 grams. Now, if that's challenging your chemistry sensibilities because we're not talking about a specific molecule like a tannin or a pollutant or something, this just gives you a ballpark idea of how much is possible. So you end up getting, if you do the math there, 8.2 times 10 to the minus third grams of CH2O, which then is just 8.2 milligrams of organic matter. So most of these things, we just want a ballpark figure. So under these conditions of oxygen, how much organic matter can be oxidized? It's a useful calculation. It's just a ballpark. Now, if we wanted to know how many milligrams of a specific chemical, that's fine, but we would have to know what the concentration of that chemical is in the water. That would be a much more complicated calculation. Plus, the oxygen doesn't discriminate between one type of organic matter and another. It's over time, it's oxidizing all of that matter. And that's something we need to consider. Okay, let me just kind of take a look and see how much longer we want to do this video. So far this is what? I'm not even sure how long this is, but I'm going to stop this one here. Chapter 10, as I told you before, is a beast of a chapter. So maybe we'll chop this up into some smaller chunks here. So we will then move on next to jumping actually to do another problem, and this one is redox. So number 10-5. So if you want to try that 10.5 on your own, this is a very important equation, but I'll talk about that here in a minute.